Hey, good morning. Today we're looking at lesson 4, talking about derivatives of inverse functions. First, we want to go back and talk about the fact that an inverse function is when any function is one-to-one, passes the horizontal line test. We know from past courses that this is the test to tell us we have a unique inverse function. And you should recall that inverse functions undo each other. In fact, if we have a composition of a function, the composition either f of g of x or g of f of x will lead us back to y equals x, which is the identity function. And that's how we know that two functions are inverses of each other. We also know the idea of reflective property. If a point AB is on a function f, then the point BA would be contained on the inverse of the function, because the properties of inverses is that they undo each other. X becomes y and y becomes x. So in our first example, we're going to use that reflective property on these two functions f and g, and we're going to look at the table of some values, and we're going to complete the table of values for the inverse of x. So if the function f has the ordered pair 3, 2, then we know the inverse has the ordered pair 2, 3. And in our next point, 1, -1, then the inverse would have -1, 1. So just to kind of refresh our memory here about what inverse functions look like. The same goes for g of x. On the function g, the ordered pair is 3, -1, so our inverse would contain the point -1, +3. And then completing the table for the inverse, we have these ordered pairs. So in the next two cases, we're going to use those tables to calculate a couple of examples. Here we want to find the value of f of g inverse of 0. So I want to look at what the g inverse of 0 is, and we can tell the g inverse of 0 is +1. So completing this composition, the f of 1, I believe that was -1, wasn't it? The f of 1 was -1 here. On letter D, the f of -1, the f of -1 is 4. So the f inverse of 4 is -1. They just undo each other. On E, g inverse of -1, g inverse of -1 is 3. And then we want the f inverse of 3. And let's go look at that. The f inverse of 3, well, we don't know what the f inverse of 3 is because it's not defined. So that is not defined on our table. We don't have enough information to complete that portion of the composition. That's going to tell us the f inverse of the g inverse of -1 is also not defined. So we can't complete that task. And lastly, the f inverse of 4 we said was -1 from example D. So the g inverse of -1, the g inverse of -1 is 3. And there we have just kind of a brief look back at reflective properties of inverse functions and how they can be calculated using tables. So if a function has an inverse, if and only if it's 1-to-1, and if f is strictly monotonic on its entire domain, that means it's increasing everywhere or it's decreasing everywhere, then it's going to be 1 to 1 and therefore has an inverse function. That's a handy little fact to know. So the relationship, we're going to prove this here. The relationship says that if we do f inverse of x, we're going to get x. So let's first let g be the inverse function. That'll give us a little speedier notation that way. So this is going to be a proof. And we know that the f of g of x is going to give us x based on this substitution right here. So I'm just recopying this piece. And if we take the derivative with respect to x of both sides, that would look like that. And this is the composition. So my derivative is the chain rule, f prime, hold g constant, times g prime, using the chain rule. And this is dx dx, and we know dx dx gives us 1, right? So f prime g of x times g prime of x is going to be 1, and the derivative is 1 over f prime g of x. And we said g was the inverse function, so the inverse function is the reciprocal of the derivative of the function times the inverse of x somewhere on that curve. Okay, so we just proved using the chain rule and differentiating both sides, we could find a formula for the derivative of an inverse. And we just proved that the slopes are reciprocals of each other. And we'll see that in our coming examples. So let's say you're given this function, 4x minus 3, so it's linear. And we want to find, and we know that the slope at 2 is 4. And we want to find the value of the inverse at 5. Now we know the slope at 2 is 4 because we know the derivative of the function is the slope of a line anywhere on a linear function. So we know 4x minus 3 is 5. This is the y value, right? It's the x value on the inverse, so it's the y value on the function. That tells me when 4x is 8, x has to be 2. So the ordered pair is 2, 5 on my function. So you might want to make a little note of that. 5 is the y value for the function f of x. And now we know 2, 5 is the point on the function. The f of 2 is 5. And on the inverse function, they interchange, and the f inverse of 5 is 2. Okay, so if we apply the formula that we just got in our little proof over there, let's see, first we did that, second we did this, now we know this, so we're going to use the formula. Let's make a note of that. We're going to apply that formula that we just derived. And that formula said the inverse of 5 prime is 1 over f prime f inverse of 5. And what was the f inverse of 5? The f inverse of 5 was 2. And what was the slope at 2? It was 4. So the f inverse of 5, or the derivative of that, is 1/4. So you see what I'm saying back here? This formula lets me know that if I know the slope on the function, and our slope on our function in example 2, if we know the slope on the function is 4, then the slope on the inverse of the function is the reciprocal, 1/4. Slopes of inverses are reciprocals. You might want to write that down. Slopes of inverses are reciprocals. So let's say we want to find the derivative of an inverse function. Here's the procedure. And without spending time reading through that, we're just going to go look at this in a table format and experience that, okay? So we have this function f, and the ordered pair is 2, 5. And we know g of x is the inverse of f of x. So that tells me g of x is going to have the ordered pair 5, 2, because these are switched, and 3, -1 becomes -1, 3 on g, and -1, 4 becomes 4, -1. So we want to look at the fact that we're going to find the inverse of -1, right? So the inverse of -1 tells me that I can find g inverse -1 is 1 over the f prime of 3, because the inverse of -1, or g prime, I'm sorry, I'm saying inverse and reading prime. Back that bus up. We want to find the derivative of -1 on the g graph. So the derivative of -1 is the y value here, and the y value on f is the x value on g. So we know the slope is -4 on the derivative of f. So the derivative of g would be the reciprocal -1/4. Now they also wanted us to fill in the table. So if this derivative is 1 and the reciprocal is 1 over 0, then the derivative here doesn't exist. This derivative is 6, so the derivative on the inverse is 1 over 6. And I'm going to say it again, that the slopes of inverses are reciprocals. The slopes of inverses are reciprocals. The slope of f is -4, the reciprocal is -1/4. Okay? Let's see, example 4, where did all of this come from? Is that on your notes? I don't think this is actually written on your notes, but you can have that for yourself. In example 4, let g be the inverse of f, and we want to calculate the derivative at 9 for this function, this cubic function f of x. So you can either think about synthetic division, or you can think about inspection here. I see a 4 plus a 5 equals a 9, but let's just work it out mathematically. Let's say we had 4x cubed plus 5x equals, actually on your notes you have -9 here. So let's put -9 in there. And then 4x cubed plus 5x would equal 0 when I add 9. And like I said, I can either think about stuff from an inspection point of view, or I can actually use synthetic division and try a few values. So my p over q list would be plus and minus 1, plus and minus 3, plus and minus 9, and then go back and divide by 4. But I'm just going to start out with -1 because I think that's going to work for me. So 4 times -1 and -4 times -1, and 5 plus 4 is 9, and that got what I needed. Okay? So if the inverses have reciprocal slopes, So we know a 0 here, right? If inverses have reciprocal slopes, at f of -1, my y value is -9. So when the inverse is -9, we can say that the g inverse of -9 is the f inverse of 9, since they defined g to be the inverse of f. So we know this is true. And then where the derivative, let's go back and look. What's the derivative of this function? 12x squared plus 5. So the derivative at -1 is 12 times -1 squared plus 5, and that's 12 plus 5. So our derivative at -1 on the f graph is 17. And the slopes on the inverse at -9 is the reciprocal of the slope on the function. The slopes of inverses are reciprocals. Okay, so this looks like I need to go back and change this to match your student notes. That should be a -9 there. In example 5, let's see what this says. So we're going to need a calculator. There's questions where you'll need to use a calculator to find approximations accurate to 3 decimal places. Now you know you can either truncate, that means just stop at 3, or you can use proper rounding rules and round as you see fit on the AP exam. So here's an example of this task. We've got this function and we want to find the derivative of the inverse at 3, and we need to be accurate to 3 decimal places. So this is the x value on the inverse. It's the y value over here, so the function's 3. That means I want to take 4x to the 7th minus x squared plus x minus 5 and set that equal to 3. And I'm using an Inspire, so I can actually pull up my Inspire and I can use that to solve. So this has a solver, and we can enter 4x to the 7th minus, we're up in the air, minus x squared plus x minus 5 equals 3, put comma x so it knows what we're solving for, and we have this value. So if you want to, you can store that. I'm storing it into letter A, and normally I would have more values than that. I didn't set my truncation far enough, my decimal set, but we'll leave it at that for a minute. And then we want to find, so we'll go back to this, we want to find I think it rounded to 4 right there, but I have lots of extra values here. And I would store that longer value by changing my calculator to have more digits floating behind the decimal. So the derivative is 28x to the 6th minus 2x plus 1, and we want to know what the derivative of our stored value is going to be. So we want to go back to that on the calculator. So we're going to look at menu for derivative at a point, and my value is stored in a. I want the first derivative, and I'm using, I should have put the graph in there, 4x to the 7th minus x squared plus x minus 5. So that's a little tip on your AP exam to speed up. Just always graph the function. Whoops, something happened. Okay, let's see. Let's try that again. We'll do it I want the derivative at a point. We'll put the point in. 1.10639588. Okay, I want the derivative of 4x to the 7th power minus x squared plus x minus 5. And it's about 50.1468. So we got 50.1468. So the derivative, or the f inverse of 3, because remember this was my y value on the f graph, so it's the x value on the derivative graph is 1 divided by 50.1468. So we can go back and calculate that. 1 divided by 50.1468. And that derivative is 0.19941. So like I said, when you get to the end, then you round your answers. Always have 5 or 6 digits behind the decimal. Or if you're lucky enough to have a really fancy calculator like the Inspire, you can store those. Like I said, I like to put 12 digits floating behind the decimal. I forgot to preset that up. So to be accurate to 3 decimal places, you want 3 digits behind the decimal. You could either just write the answer and move on, or if you want to just leave 3, they would accept that answer, or they would also accept 0 to 0. This is important. This tells me that I rounded up from that 4th digit. Okay? Now you can also find derivatives of other bases like a to the x and log base a of x, or a to any power, where you've got to use the chain rule because you're taking the derivative of that other function there. So we'll look at a few of those. In this case, to find the derivative for 3 to the x, that rule said a to the x derivative is natural log of a times a to the x, or you can say that it's a to the u, natural log of a, and then a prime, or u prime, in this case x, so the derivative of x is 1. But here I've got to think past that. So this one I might want to rewrite that to be a little more compact. Like I know 4 is 2 to the 2nd power. So we could think of the y function as being 2 to the 6x power. And that makes our natural log as small as it needs to be. Whoa, hold on just a second. I don't know why. Okay, something weird's going on. And here I want the derivative. So that's a to the u, which is 2 to the 6x. ln of a times the derivative of the u, and 6x is my u, so 6 is the derivative. So danger beware. 6 times natural log of 2, this is a constant. The 6 doesn't go to the power. You can't multiply the 6 times the 2. They're not tied together, but I can say 2 to the 6th power is 64 and then leave that to the x. So this piece I can multiply and expand out, but I can't say 6 times 2 is 12 to the 6x power. That's a common error. Don't let that happen to you. And here again, I've got a to the u power. So y prime is a to the u, ln of a, natural log of a, times the derivative of your power, which is 2x, because my u is x squared. If you like writing out u substitution, you could do that. So we got 5 to the x squared power times natural log of 5 times 2x. So if you like, you can say u is x squared and u prime is 2x. And if you're looking at y equals 5 to the u, the rule said 5 to the u, ln 5, u prime, right? So 5 to the u, ln of the base, and u prime. This one, same thing as this over here. Y prime is a to the u power times natural log of your base times the derivative of your function that's substituted in. And you can just leave it like that. Do not multiply 5 times -2. Don't make that mistake. All right, let's see. Example 7. So these are logs. Now the log rule was log base 5 of x is the 1 over the natural log of the base times the x. So y prime is 1 over natural log of the base times x. Or if you wanted to, you could put the x in front of the constant. This one, if you think about u being sine of x, then your derivative is cosine of x. And your log is log base a of u is 1 over natural log of your base times your u times your derivative of your u. So my derivative is cosine. That's in the numerator because we can multiply the 1 times the u prime. The natural log of a is the natural log of the base, so that's the constant, times your function, which was sine of x. Okay? Now, in this case, I guess you could say cosine over sine and simplify that down as cotangent, but it would be cotangent divided by natural log of 3, or you could put tangent on the bottom with natural log of 3. But I'm happy just to stop here unless it's a multiple choice and you're trying to chase down some multiple choice answer. This one, our base is 10 now because the log without any subscript means base 10. That's our common log. So we got 1 over natural log of the base times the function. And then we've got to take the derivative of the function, which is 1 plus 3 to the x ln 3. So I've got to multiply that times the fraction. So we've got 1 plus 3 to the x power natural log of 3 divided by natural log 10 times x plus 3 to the x power. Okay? I need more room to write on this one. So we're going to move down here. Log base 2. Pull this down here. I need some more room. Okay. So we got log base 2, our derivative. We're going to say u is 2x plus 1 to the 1/3 power. The derivative of that is 2 for the derivative of the inside, and then 2x plus 1 times 1/3 to the negative 2/3 power. So this is my derivative for the function substituted in. And we need to do 1 over natural log for the base times the argument to the 1/3 power times this derivative. So we've got a 2/3 with another 2x plus 1 to the 2/3. So I just moved this little piece over, this derivative, I put that into my derivative. Y prime, cleaning that up, is going to give us 2 in the top, 3 natural log of 2, and here I've got 2x plus 1 quantity to the 3/3 power, so that's a 2x plus 1. Okay? So if I lost you back here, let me go clean this up a bit. Whoop. Okay, so we had originally 1 over natural log of 2 times 2x plus 1 to the 3rd times the derivative, which was 2 over 3 times 2x plus 1 to the 2/3, using the power rule and the chain rule. Ended up with this monstrosity. Couple more. So example 8, we want to find an equation for the tangent line for the function f of x equals 6 to the x power, where x is 2. So first I need to find if f is 2, the point is 36, 6 squared is 36. I need a point and a slope. The slope at 2 is a to the u, ln a, and u prime is 1. So 36 natural log of 6. And on our calculator, 36 natural log of 6 is just about 64,5033,408. So big slope. The tangent line, exactly if I want the tangent line just written out without approximations, I could have y equals 36 natural log of 6 is the slope, x minus 2 plus 36, or I could give it as an approximation if I needed it, and it would be 64,503 x minus 2 plus 36. And really it just depends on how you needed that format for a number or for a multiple choice. Excuse me. Here we have a practical application. A bacteria is growing according to this function, and W of t is the weight of the culture in ounces. T is in hours. Find the weight of the culture after 0 hours, 2 hours, 8 hours. What's the limit? So we want to look at the W of 0. I've already pre-done that. That was 1. The weight at 2. You can check my work on your calculator. I got this amount. Whoop, something happened to my 5 there. The weight at 8 hours is about 1.28429. And we want the limit as t approaches infinity on that function. And it looks like as we go farther and farther, it's going to 1.3. And they've asked us, what is that limit? Well, that would be the carrying capacity for the logistics growth behavior model, because this is a logistic curve. It's going to look like that. And this numerator, if you remember from pre-calc, that's my limit or carrying capacity. So I could say the limit's approaching 1.35. And then our last example is back to using tables. We can use the table to fill out the rest of the ordered pairs for the inverse in this column over here. So the inverse would be 5, -3 on G, so because this is the ordered pair 3, 5 on the G graph, so 5, -3. I'm just flipping this column and this column. And that'll make our work here in these examples a little speedier. Okay, so here we go. We want to find the F inverse prime of 4. So our notation's a little cumbersome sometimes. The F inverse prime at 4 is 1 over the F prime. See, at 4, this is the Y value on F, so it's the X value on the inverse. So the F prime of 2 would be the X, and that slope is 1, so we have 1 divided by 1. That means my slope at 4, the slope at 4 on the inverse function is 1. So we want the derivative at 3 on the inverse, or -3, I'm sorry. The derivative at -3 on the inverse function is 1 divided by -3 on G. So -3 is going to be 2 on the G graph. So the G prime at 2. And here's 2. The G prime at 2 is 2. So the slope on the inverse of G at -3 is 1/2, because the slope at 2 on the G graph is 2. The slopes are reciprocals. Write the equation for the tangent line to the graph of G inverse of X when X is 2. Well, we just saw the G inverse of 2. Let's go back and look. The G inverse of 2 is 4. And what's our slope? At 2, it would be 1 over G prime at 4. So G prime at 4 is -3, right? Is -3. So our tangent line, we've got a point and a slope. The tangent line is y equals -1/3 x minus 2 plus 4. So let me mention something to you here. This is an alternate method. You might like it better. You know that the G of 4 is 2, and you know that the G prime at 4 is -1/3, is -3. So the G inverse of 2 is the reciprocal. And if you can get your brain thinking about it this way, it saves you all of that notation, unless you had to write that notation for a free response. So our last example, we want to estimate the value of G prime of 3 and use the result to explain the behavior of the graph of the function G when X is 3. So we know that the g of 3 could be, let's go back to our table and erase some of this. The g of 3, we don't have 3. We don't have 3 on our x values here. So we could use the difference between 4 and 2, right? So let's go to that. We could say the g of 4 minus the g of 2 divided by 4 minus 2. So we're doing the change in y over the change in x, taking the average between 4 and 2. And this was 2 minus negative 3 divided by 2. So our slope at 3, the rate of change, the derivative, the instantaneous rate of change, is 5 over 2. So what do we know about the function g? Since the derivative is positive, what can we say? The graph of g would be increasing because our derivative is positive at that point. X equals 3. And that gives us a little insight into things coming up in the future. Okay, that's a long lesson. See you next time, one more lesson.